Hi folks, today we're going to have a look at the 2018 Higher Physics paper section 1, the multiple choice questions. So without any further ado, let's make a start. Question number 1 says a car is moving at a speed of 2 meters per second. The car now accelerates at 4 meters per second until it reaches a speed of 14 meters per second. The distance travelled by the car during this acceleration is, well, it's a SUVAT question. S is the distance that's travelled, that's what we want to know. Question mark. U is the initial speed, which is 2 meters per second. V is the final speed, which is 14 meters per second. A is the acceleration, which is 4 meters per second. And T, the time we don't know anything about. This formula is probably the easiest one to use. We've got U, V, and A, and we want to know S. So we put the numbers into that formula, like so, and rearrange it to get the final answer of 24 meters, which is answer C. Question 2. A ball is dropped from rest and allowed to bounce several times. The graph shows how the velocity of the ball varies with time. A student makes the following statements about the ball. Firstly, that it hits the ground at P. Secondly, that the ball is moving upwards between Q and R. And thirdly, that the ball is moving upwards between R and S. So let's have a look at what the situation really is. Here's the ball falling down, bouncing upwards, getting to a high point, and then falling back down again, and then repeating. So when the ball is falling down on its downward motion, you can see the graph is in the positive side of the axis. When it's moving upwards on the upward bounce, it's on the negative side of the axis. So anything moving downwards is a positive velocity. Anything moving upwards is a negative velocity. Whenever the line crosses the x-axis, or the time axis here, then it changes direction. So the statements. The ball hits the ground at P. Well, between O and P, that is the ball falling and then colliding with the ground. So that's correct. The ball is moving upwards between Q and R. Well, yes. When it leaves the ground at Q, it moves upwards until it gets to its highest point at R, where its speed instantaneously drops to 0. And then the ball is moving upwards between R and S. Well, it can't be. If the ball is moving upwards between Q and R, and remember we said anytime the line crosses the axis, it changes direction, then it can't also be moving upwards between R and S. Indeed, once it's got to its highest point at R, it begins to fall downwards again until it hits the ground at S. So that is incorrect. So 1 and 2 are correct. Answer D. Question number 3. A block of mass 6 kilograms and a block of mass 8 kilograms are connected by a spring. A force of 32 newtons is applied to the blocks as shown. The frictional force of 4 newtons acts on each block. The acceleration of the 6 kilogram block is, well, first thing we need to realize is that the two things are tied together. So they're going to be accelerating together. So if the 6 kilogram block is accelerating at a certain rate, so is the 8 kilogram block. And in fact, the two things together are accelerating at that rate. So what we're actually trying to calculate is not the acceleration of the 6 kilogram block, but actually the acceleration of the whole system together. Now, we know that each experience 4 newtons worth of friction. So that gives us a total frictional force of 8 newtons. There are 2 objects here, and remember we're trying to work out the acceleration of the whole system. So the whole system's mass is 6 plus 8, which is 14 kilograms. And now we can use Newton's second law to figure out our answer. F equals ma. Remember that F in F equals ma stands for the unbalanced force. So if there's 32 newtons pulling one direction and 8 newtons pulling the other direction, the unbalanced force is the difference between those. 32 minus 8 equals the mass, which is 14, times acceleration. Acceleration, 32 minus 8 divided by 14, is 1.7 meters per second per second. Answer A. Number 4. A person stands on a weighing machine in a lift. When the lift is at rest, the reading on the weighing machine is 700 newtons. The lift now descends and its speed increases at a constant rate. The reading on the weighing machine, all right. So if you get in a lift and the lift accelerates downwards, then it's almost as if the floor of the lift drops away from you. So you feel a bit lighter. You're pushing less hard on the floor and the floor is pushing less hard back up on you. Because it's accelerating at a constant rate, though, you would feel constantly lighter. So the answer is going to be B. They will feel a constant value less than their normal weight of 700 newtons. Number 5. Enceladus is a moon of Saturn. Its mass is 1.08 times 10 to the power of 20 kilograms. The mass of Saturn is 5.68 times 10 to the power of 26 kilograms. The gravitational force of attraction is 7.24 times 10 to the power of 19 newtons. The orbital radius of Enceladus around Saturn is... So, this is a straightforward stick the numbers in the formula question. We use our inverse square law of gravitation, F equals gmm over r squared. G is the universal gravitational constant, which you can get from your data sheet, 6.67 times 10 to the minus 11, times the two masses together, divided by their square of the radius. So the radius is going to be the square root of the overall force divided by the product of the gravitational constant multiplied by these two masses, which is 2.38 times 10 to the power of 8 meters, which is answer A. Number 6. A spacecraft is traveling at 0.1 c relative to a star. An observer on the spacecraft measures the speed of light emitted by the star to be... A little bit of a trick here, because what we need to remember is that the speed of light is the same for all observers, regardless how quickly they are moving relative to the source. Therefore, the answer is C, 1 times the speed of light. Number 7. A spacecraft is traveling at a speed of 0.2 c relative to the Earth. The spacecraft emits a signal for 20 seconds and as measured in the frame of reference of the spacecraft. An observer on Earth measures the duration of the signal as... So this is a time dilation question. T dash equals T over the square root of 1 minus V squared over C squared. People get confused about which one is T and which one is T dash. The T dash is the one that is moving relative to the other one. So in this case, the Earth is moving relative to the spacecraft. The signal being measured in the spacecraft is not moving with the spacecraft. It's effectively stationary with the spacecraft. So it's T dash we're trying to work out here, which, if we put the numbers into that formula, we get 20.4 seconds. Answer D. Number 8. How many types of quark are there? Well, here's a standard model. And on the top left, you can see the quarks. There is the up, down, charm, strange, top and bottom, which makes 6. Number 9. An electron is a... Well, let's get the standard model back again. Look for electrons. There they are, bottom left, in amongst the leptons. Answer E. Question 10. A proton enters a region of magnetic field as shown. On entering the magnetic field, the proton will... Right. This is one of these hand rules questions. Now, the way I remember which hand to use, I think in electricity, it's the electrons that move. Electrons are negative. So the right way to think about the current is electrons, negative. So our right hand is for negative charges. In this case, though, It's a proton, which is positive. So we're going to use our left hand. And you can see there, if I take my left hand and hold my first finger at right angles to my second finger, which in turn is at right angles to my thumb, then I can work this out. So first finger field, my index finger points into the screen. Second finger current, that is the movement of the proton as it enters the magnetic field, which in this case is from left to right. So my left hand is pointing with my index finger into the screen. My second finger, the current, is pointing from left to right, and my thumb, which is the thrust of or motion or force, however you want to think of it, is going to be pointing upwards. Therefore, the answer is C, deflects towards the top of the page. Number 11. A nuclear fission reaction is represented by the following statement. The nucleus, represented by X, is... Okay, so what we need to have here, we've got a neutron coming in and bombarding a uranium nucleus. And that is separating down into two elements along with 3 neutrons. So what do we need to do? Well, we need to have the numbers on both sides of the arrow adding up to each other. So the first number, the nucleon number, the number at the top, is going to be, on the left-hand side, 235 plus 1, which is 236. On the right-hand side, it must also add up to 236. So the value for X is going to be 236 minus 141 from the barium and minus the 3 from the 3 neutrons. And my atomic number, again, they have to add up on both sides. So on the left-hand side, the total atomic number is 92. On the right-hand side, the total atomic number also has to be 92. 56 from the barium, therefore the remainder must be in our unknown element. So if we do those sums, we end up with 92 and 36. And if we look for atomic number 36, we'll see it's krypton. Answer B. Number 12, the radiance on a surface 0.5 meters from a source of light is I. The radiance on a surface 1.5 meters from this source is... Okay, so this is an inverse square law question. So the formula is this, I equals K over D squared. K just stands for any constant. I don't know why physicists insist on using K for a constant. Maybe they just can't spell. Anyway, what that means is, if we rearrange that a little bit, is that the irradiance multiplied by the square of the distance from a point source is always equal to a constant. So we can write this formula like this. I1 D1 squared equals I2 D2 squared. So in this case, my initial irradiance is 1I, and my distance is 0.5. So 1 times 0.5 squared on the left-hand side. On the right-hand side, my new distance is 1.5. So I2 times 1.5 squared. Do a little bit of rearranging. I2 is going to be 1 times 0.5 squared divided by 1.5 squared, which gets me 0.11 I's worth, which is answer A. Number 13. Waves from two coherent sources, S1 and S2, produce an interference pattern. Maxima are detected at the positions shown below. The path difference S1P to S2P is 154 millimeters. So, as we can see there, we're at this point P, which is obviously a little further from source 1 than it is from source 2. It is 154 millimeters further from source 1 than from source 2. These are maxima, so we use this formula. Maxima are where we get constructive interference. So the path difference is equal to m lambda. The path difference we're given, m is the number of maxima. So the dotted line along the center is the 0 maxima. And then as we count downwards from that dotted line along the middle, we get 1, 2, 3, 4, 5 dots when we get to P. So M is 5. So our path difference is 154, M is 5. So 154 equals 5 lambda. Lambda is 154 over 5, which is 30.8 millimeters. Answer D. Number 14. A ray of monochromatic light passes from air into a block of glass as shown. The wavelength of this light in air is 6.3 times 10 to the minus 7 meters. The refractive index of the glass for this light is 1.50. The frequency of this light in the glass is... Okay, so we're told the wavelength in air and we're told the refractive index. What we need to understand is that the frequency of the light does not change as it moves from one material to another. As the light goes from air into glass, its speed will decrease and its wavelength will decrease by the same factor. So the frequency, which is the ratio of speed to wavelength, is going to be constant. The frequency does not change. So if we work out the frequency of the light in air, we have worked out the frequency of the light in the glass as well. So all we need to do is use F equals V over lambda, where V is the speed of light, 3 times 10 to the power of 8, divided by the wavelength, which is 6.3 times 10 to the power of minus 7, and that gets us a frequency of 4.76 times 10 to the power of 14 hertz in air and in glass. Answer D. Number 15. The circuit is set as shown. A battery has negligible internal resistance. A student makes the following statements about the readings on the meters in this circuit. So when switch S is open, the reading on the voltmeter will be 6 volts. So when switch S is open, that's effectively like that bottom 10 ohm resistor not existing at all. And therefore, we've just got 2 10 ohm resistors in series. If we've got 2 identical resistors in series, then the supply voltage will be split equally between the 2. So in this case, the supply voltage is 12. The voltage across each of the 2 10 ohm resistors would be 6. So that is correct. 2. When switch S is open, the reading on ammeter A2 will be 0.6 amps. But when the switch is open, the ammeter reading is going to be controlled by the resistance of both the resistors. So I equals V over R. Voltage, the supply voltage is 12. The resistance is 2 10 ohm resistors, which is 20, which gives 0.6 amps. Correct. 3. When the switch S is closed, the reading on ammeter A1 will be 0.8 amps. Right. A1 is the current leaving the battery. So what is going to happen here? Well, when the 2 10 ohm resistors now are in parallel with each other, they have a combined resistance of half as much as one on its own. A useful little rule to remember. 2 identical resistors in parallel will have a combined resistance of half as much as one on its own. So these 2 10s will have a combined resistance of 5. Therefore, the whole circuit's resistance will be 15 ohms. I equals V over R, 12 over 15, which is 0.8 amps. Correct. All 3 of these statements are correct. Answer E. Number 16. Power dissipated in a 120 ohm resistor is 4.8 watts. The current in the resistor is, so we've got resistance, we've got power, we want to know current. We'll use this formula, P equals I squared R. Stick our numbers in the formula, rearrange it, and we get 0.2 amps. Answer C. Number 17. A 24 microfarad capacitor is charged until the potential difference across it is 125 volts. The charge stored on the capacitor is... So, C equals Q over V is our formula. I remember Q equals CV. I just remember CV. Anyway, we're trying to work out charge. So we multiply our capacitance, which is 24 microfarads, or 24 times 10 to the power of minus 6, times the voltage, or the potential difference, 125 volts. And that gets us a charge of 3 times 10 to the power of minus 3 coulombs. Answer D. Number 18, a circuit is set up as shown. When the capacitor is fully charged, the energy stored in the capacitor is, well, when the capacitor is fully charged, the voltage across the capacitor is the full supply voltage, which is 12 volts in this case. We have 3 formulas in our formula sheets, all lumped into one for the energy in a capacitor. Here we've got capacitance and voltage, but know nothing about charge, so we'll use the middle one. E equals a half CV squared. Put the numbers into that formula. So a half times 220 microfarads, 220 times 10 to the minus 6, times 12 squared. Don't forget the squared. And we get 0.016 joules, or 1.6 times 10 to the power of minus 2 joules. Answer D. Number 19. The circuit shown is used to charge and then discharge a capacitor C. Which pair of graphs shows how the potential difference V across the capacitor varies with time during charging and discharging? So here's a little animation. And as you can see here, as the capacitor charges, the current drops from a high value to 0, while the potential difference, the voltage, increases from 0 up to the supply voltage. When the capacitor discharges, the current drops from a high negative value to 0, and the voltage drops from the supply voltage back down to 0. So the 2 graphs that we need to be concentrating on for this question are the 2 on the right-hand side here. The voltage charging, rising, and then leveling out, and the voltage while discharging, dropping down to 0. So that gets us answer E. And the last question, a student carries out an experiment to determine the specific heat capacity C of a solid. The relationship used to calculate C is that, which you might remember from National 5. The recorded measurements and their percentage uncertainties are shown. A good estimate of the percentage uncertainty in the calculated value of C is, so at higher, all that we need to understand is that when we combine values, the uncertainty in the combined value is the largest percentage uncertainty of the values used to make that value. So in this case, the biggest one is that one. Change in temperature, 5%. Therefore, the estimate of the percentage uncertainty in the combined value will also be 5%. Answer C. And there we have it. That's the 2018 multiple choice questions from section 1. I hope that was helpful, and I'll talk to you again some other time.